Here is a combined summary of the 2 pages. The paper introduces a model-based super-resolution framework, Model SR, to address the ill-posedness of the super-resolution problem, which involves acquiring high-frequency data from low-frequency measurements. This framework recovers the signal by solving a nonlinear least square problem, achieving super-resolution. Theoretically, the resolution-enhancing map is proved to have Lipschitz continuity under mild conditions, leading to a stable solution to the super-resolution problem. Super-resolution has been a central problem in imaging systems for centuries, limited by the diffraction nature of the wave. The resolution limit can be characterized by Rayleigh length and depends on the cutoff frequency of the system. Traditional subspace methods, such as music, esprit, and matrix pencil, have been developed for high-resolution point source reconstruction. Compressive sensing has also motivated sparsity exploiting algorithms for super-resolution. Despite the vast literature on super-resolution, few theoretical works have been done beyond the point source model. Recent studies have introduced the concept of computational resolution limit, characterizing the resolution limits for computational methods in the presence of noise. In computer vision, single-image super-resolution (SISR) methods have been widely explored, including example-based strategies and deep learning approaches. The proposed Model SR framework can be extended to problems with similar structures. The author's contribution lies in developing the mathematical theory of the Model SR framework. By adopting the idea that the signal space can be modeled by a low-dimensional parameter space, the numerical method for solving the super-resolution problem contains 2 steps: recovering the signal by solving a nonlinear least square problem and then obtaining the resolution-enhanced signal by straightforward sampling. Here is a combined summary of pages 3 and 4 of the research paper. The paper introduces a model-based super-resolution framework, denoted as Model SR, which aims to recover high-resolution signals from low-resolution measurements. The framework is locally Lipschitz stable under mild conditions, and several specific models are discussed under Model SR. The point source model is analyzed, and a stability estimate is derived, showing that exact recovery of point sources from noiseless low-resolution measurements does not require a minimum separation distance condition. The discussion is extended to signals with a finite rate of innovation and signals with a specific continuous form in the physics domain. The paper is organized into 9 sections, with Section 2 introducing the model-based super-resolution framework, Section 3 focusing on the mathematical theory, and subsequent sections discussing specific models and numerical experiments. The notations used throughout the paper are defined, including the L2 norm, operator norm, Dirac measure, Frechet derivative, and Fourier transform. The model-based super-resolution framework is developed, with the mathematical model presented in Section 2.1. The framework involves a low-resolution sampling operator GL and a high-resolution sampling operator GH, which are assumed to be continuous. The super-resolution factor, SRF, is defined as the ratio of the high-resolution sampling points to the low-resolution sampling points. The signal space is defined as an equivalent class, where 2 signals are considered equivalent if they have the same sampling values. The low and high resolution signal spaces are denoted as HL and HH, respectively, and a downsampling operator Q is defined to satisfy the commutative diagram in Figure 1. The goal of super-resolution is to find a resolution-enhancing map L that satisfies the condition L hollow bullet GL equals GH. Overall, the paper presents a comprehensive framework for model-based super-resolution, with a focus on the mathematical theory and specific models. The framework is developed to recover high-resolution signals from low-resolution measurements, and numerical experiments are conducted to test the proposed method. In the context of super-resolution, the authors propose a consistency condition, Condition 1, which states that the low-resolution sampling operator GL must be injective to ensure the well-posedness of the super-resolution problem. This condition implies that the signal profile can be determined from the measurement, and its lack leads to the non-uniqueness of the super-resolution problem. The authors introduce a model-based super-resolution framework, where the signal space omega is regarded as a finite-dimensional manifold embedded in the infinite-dimensional space S, R. A modeling pair, theta, P, is defined, where theta is a compact parameter space and P is a surjective and continuous map from theta to omega. The low-resolution map PL and high-resolution map PH are defined as GL ring operator P and GH ring operator P, respectively. The authors further define the intrinsic dimension of the signal space omega as the dimension of the parameter space theta, which satisfies certain local bijection properties. A remark is made that the intrinsic dimension is defined through local bijection instead of global bijection due to the symmetry property of the model map P. In practice, the exact intrinsic dimension of the signal space may not be available and needs to be estimated. To address this, the authors introduce the concept of compatibility for the case when the dimension of the parameter space is larger than the intrinsic dimension of the signal space. A compatible modeling pair, theta, p, and theta, p, is defined, where theta is a higher dimensional parameter space and p is a continuous surjection from theta to a higher dimensional signal space omega. The compatibility condition is satisfied if a certain commutative diagram holds, ensuring that the modeling pairs are consistent with each other. Examples are provided to illustrate the concepts, including a simple example of a modelable signal space omega-1 and a demonstration of the compatibility condition. The author's framework provides a theoretical foundation for model-based super-resolution and offers a way to estimate the intrinsic dimension of the signal space. Here is a combined summary of pages 7 and 8 of the research paper. The authors define the low-resolution map $P_L$ and high-resolution map $P_H$ using the modeling pair $theta, P$. The low-resolution sampling operator $G_L$ ensures the injectivity of the signal, allowing for unique signal recovery from low-resolution measurements. The numerical methodology for the super-resolution problem involves two steps: estimating the parameter $theta by solving a non-convex optimization problem, and obtaining the resolution-enhanced signal by calculating $P_H theta. The optimization problem involves minimizing the objective function $phi theta equals frac 1 2 nabla_db P_L theta y caret $2. To ensure uniqueness of the recovered signal, the assumption $2 plus 1 greater than dim theta is required. The authors also develop a fundamental mathematical theory under the model-based super-resolution framework, including a stability estimate. The stability estimate is derived using the local property of the low-resolution map and the Lipschitz continuity of its inverse. The authors prove Theorem 3.1, which states that for every $theta in U there exists $C_U greater than $0 such that $theta lec C_U C dot P_L theta P_L theta $. They also provide a corollary, which gives a Lipschitz stability estimate for $theta, sigma, admissible parameters. The authors introduce the concept of $theta, sigma, admissibility, which is defined as $P_L theta y less than sigma where $y is the noisy low-resolution measurement. They show that the parameter theta that is slightly perturbed from theta caret is also theta sigma admissible, and therefore the Lipschitz stability estimate holds. The research paper discusses the stability and optimization aspects of a resolution-enhancing map. It starts by introducing a theorem that establishes a stability estimate for the map, which is crucial for understanding its behavior. The theorem relies on the Lipschitz constant Cu and the bound for Ba nabla dBLDPH, Ba nabla dBlop, both of which are of great importance. The stability result is then used to analyze three concrete signal models, highlighting the relationship between the stability of the resolution-enhancing map and the super-resolution factor, SRF. The paper also delves into the optimization problem, focusing on the local properties of the objective function. A theorem is presented, showing that the objective function is locally nu convex and nu smooth in the neighborhood of the solution, provided certain conditions are met. This analysis is significant for understanding the behavior of the resolution-enhancing map and its applications in signal processing. In the context of super-resolution, the point source model is considered, where signals are generated by n sources in the interval 0, 1, with amplitudes taking values in a closed interval I subset of AI. The model map is defined as p theta equals psi x equals n array summation nj equals 1 theta j 1 delta theta j 2, where theta j 2 represents the position of the point sources, and theta j 1 the corresponding amplitude. The intrinsic dimension of the signal space is 2n. The low and high resolution sampling operators, GL and GH, can be defined by equations 2.2 and 2.3, respectively. Consequently, the noisy low-resolution measurement can be expressed as yk equals gk plus weak equals n array summation nj equals 1 theta j 1 e caret 2 pi I theta j 2k plus weak k equals kl where weak is the noise term with weak less than sigma. We assume that kl is greater than or equal to n. The Rayleigh length of this system is defined as RL equals half a kiloliter. In this section, we consider signals generated by n different point sources. We assume that theta j 1 does not equal 0 and theta j 2s are pairwise different. Otherwise, the signal space has an intrinsic dimension less than 2n, and one should consider the corresponding representation pair. We have the following theorem on the stability estimate. Theorem 4.1 states that for any given theta asterisk operator equals theta asterisk operator 1, theta asterisk operator n, 1, theta asterisk operator 1, 2, theta asterisk operator n, 2, element of theta. Let delta equals 1/2 minp does not equal q, theta asterisk operator p, 2 theta asterisk operator q, 2, and u equals n array product nj equals 1b, theta asterisk operator j, 1, theta asterisk operator j, 1, 2, intersection I times n array product nj equals 1b, theta asterisk operator j, 2, delta. Then, there exists Cu greater than 0 such that for any theta, element of theta, nabla theta, nabla is less than or equal to Cu nabla pl, theta, place, theta, nabla. Further, we have nabla dph nabla 2 op is less than or equal to 2kh plus 1, n plus 4 n pi 2a 2i, 3, kh plus 1, 2kh plus 1, define C, 2. By letting Q equals CuC, we have nabla pH, theta, phosphorus monohydride, theta, nabla is less than or equal to Q nabla PL, theta, place, theta, nabla. As a consequence, if theta element of UBA, theta, sigma, admissible parameter, then nabla pH, theta, phosphorus monohydride, theta asterisk operator, nabla less than 2Q sigma. We point out that theta asterisk operator in the above theorem can be determined exactly from the low-resolution measurement for the noiseless measurement. This implies that the signal p, theta asterisk operator, can be exactly recovered. We also notice that the result can be extended to the case when the sources have complex amplitudes. These observations indicate that within the proposed framework, the exact signal recovery does not require minimum separation distance condition nor the conditions on source signs for the noiseless measurement. This is to be contrasted with the BLASSO strategy, for which counterexample exists for sources having arbitrary sign and separation distance below 1 RL, 22. Further, the stability result offers a perspective on how the L2 error of high-resolution signal depends on noise. In the context of signals with a finite rate of innovation, Fry, we consider the super-resolution problem, focusing on signals generated by derivatives of Diracs. The model map is defined as p, theta, equals psi, x, equals r, summation display r equals 0 nr, summation display j equals 1 theta r, j, 1 delta, r, theta r, j, 2, where theta equals theta 1, 0, 1, theta nr, r, 1, theta 1, 0, 2, theta nr, r, 2. For the grid omega k equals k, we have gk equals r, summation display r equals 0 n r, summation display j equals 1 theta r, j, 1, minus 2 pi I k, re minus 2 pi I theta r, j, 2k. The noisy low-resolution measurement can be expressed as yk equals gk plus weak, where weak is the noise term with weak less than sigma. We assume that kl is greater than or equal to n. The Rayleigh length is defined as RL equals half a kiloliter. Applying theorem 3.1 and corollary 3.2, we have the following stability estimate. For any given theta asterisk operator, let increment r equals 1/2 minp, negation slash equals q dt, theta asterisk operator r, p, 2, theta asterisk operator r, q, 2. We assume that theta asterisk operator r, j, 1, negation slash equals 0, forge equals 1, and r equals 0, r, and increment r greater than 0. Let u equals product text rr equals 0, product text nrj equals 1, parent left igb, theta asterisk operator r, j, 1, theta asterisk operator r, j, 1, 2, intersection I, parent right ig times, product text rr equals 0, product text nrj equals 1b, theta asterisk operator r, j, 2, increment r. Then, there exists cu greater than 0 such that for any theta, element of theta, nabla dBl theta minus theta, nabla dBl is less than or equal to cu nabla dBl pl, theta, minus place, theta, nabla dBl. Furthermore, we have nabla dBl dph nabla dBl 2op is less than or equal to kl, summation display k equals minus klr, summation display r equals 0 nr, 2 pi k, 2r, parent left big 1 plus 4 pi 2 k 2 a 2 I, parent right big define c, 2. By letting q equals cuc, we have nabla dBl ph, theta, minus ph, theta, nabla dBl is less than or equal to q nabla dBl pl, theta, minus place, theta, nabla dBl. As a consequence, if theta element of U is a theta sigma admissible parameter, then nabla dBl ph, theta, minus ph, theta asterisk operator, nabla dBl less than 2q sigma. This is a stability estimate for the super-resolution problem in the context of Frey signals. The paper discusses the super-resolution problem for signals with continuous profiles in the physics space, focusing on the stability and resolution enhancement of the proposed numerical scheme. It begins by introducing a theorem that establishes the connection between the physical and data spaces, providing a bound on the difference between the physical and data space solutions. This bound is crucial for understanding the stability of the super-resolution problem. The paper then moves on to discuss the numerical experiments conducted to test the proposed method. Two groups of experiments are presented, one focusing on the point source model and another on signals with a finite rate of innovation. In the point source model, the authors demonstrate the stability of the proposed method by conducting 20 random experiments with varying source amplitudes and noise levels. They also show that the method can achieve resolution enhancement in the physics domain using inverse Fourier transform, IFT. Furthermore, the authors demonstrate that the proposed method does not require the separation condition for noiseless source reconstruction. They provide an example where 2 point sources with a very small separation distance are successfully distinguished and estimated. The paper concludes by highlighting the importance of appropriate modeling in achieving stable solutions to the super-resolution problem and suggests that choosing between physics-based or data-driven models remains an open question. Overall, the paper presents a comprehensive analysis of the super-resolution problem, providing insights into the stability and resolution enhancement capabilities of the proposed numerical scheme. The research discusses the enhancement of signals in the physics domain using resolution enhancement techniques. Figure 5 illustrates the original signals and their enhanced versions, showcasing the effectiveness of the method. The numerical experiment involves a noiseless signal with a specific form, including monopole, dipole, and quadrupole sources. The sources are positioned to have comparable low-resolution signals. Figure 7 demonstrates the reconstruction results, highlighting the small absolute position reconstruction error for the quadrupole source. This is attributed to the sensitivity of the loss function to higher-order poles. To visualize the resolution-enhanced signal, the Dirichlet kernel is introduced, and its convolution with the derivative of Dirac leads to increased resolution. The study also presents the reconstruction for closely positioned point sources in Figure 6 and a box plot of source positions reconstruction error for different types of sources in Figure 7. Overall, the research showcases innovative methods for signal enhancement and source reconstruction in the physics domain. The research paper discusses the amplification of signal strength using Dirichlet kernels, which is crucial for resolving sources in the physics domain. It is demonstrated that different orders of Diracs generate signals of different amplitudes in the physics domain. The experiment results show a stable reconstruction of the source positions, and the extrapolation in the frequency domain results in reliable resolution-enhanced signals in the physics domain. The paper also explores more complicated signals, specifically linear combinations of components having a specific form. The signal can be written as a sum of these components, with each component having different parameters. The experiment considers a signal with 4 components and aims to recover high-frequency data to achieve super resolution. The signal is written in an equivalent form, and different parameters are set for each component. In the physical space, 0, 1, a grid is set up for calculation of the fast Fourier transform, FFT. Noisy low-frequency data are generated, and the associated grid has a step size of 1/31. The parameters are solved by the low-frequency data, and the signal is visualized on 2 finer grids with step sizes of 1/127th and 1/4095th, respectively. The initial guess of the parameters is obtained by adding or subtracting a constant around 0.07 to the ground truth. The paper visualizes the signals in the physics domain, showing the original signal and resolution-enhanced signals. The blue line in all figures represents the signal profile calculated by inverse FFT using the original, extrapolated Fourier data. The red line in some figures shows the ground truth of point sources or the signal profile of the ground truth higher pole sources sampled by the corresponding Dirichlet kernel. The signal-to-noise ratio, SNR, of the experiment is 30.16. The research paper discusses the application of a model-based super-resolution framework in the physics domain, focusing on the interpolation of recovered signal profiles. It presents experiments with varying super-resolution factors, SRF, to enhance signal resolution. The results demonstrate improved signal quality with finer grid resolutions. The paper also extends this framework to data completion and deep learning-based super-resolution, highlighting the potential for similar structures in other problems. In the data completion section, it illustrates the use of partial and full sampling operators to develop a model-based framework. For deep learning, it draws parallels between the model SR and generative models, emphasizing the importance of learning the map from the latent space to the signal space. The discussion highlights the technical aspects of the methods, including the use of Fourier transforms and the importance of low-frequency data in parameter estimation. The overall presentation is technical and professional, making it suitable for expert researchers and stakeholders in the field. The research paper develops the theory of the model-based super-resolution framework, presenting a general mathematical theory along with concrete examples and numerical experiments. It shows that under suitable modeling, super-resolution problems enjoy certain stability. The framework's challenging part is the non-convexity nature of the objective function, requiring good initial guesses for gradient descent algorithms. Efficient methods for selecting good initial guesses are left as future work. The model-based framework can be generalized to other problems, offering another perspective on the super-resolution problem and taking a step forward in understanding model-based problems. The paper also includes an appendix with a detailed proof of Theorem 3.1, which is crucial for the stability analysis of the model-based super-resolution framework. The proof involves several steps, including the large distance case, short distance case, and a final step utilizing convexity. The entire framework is designed to provide a deeper understanding of the connection between model-based super-resolution and deep learning, highlighting the importance of efficient initial guess selection for future research. The combined summary starts directly with the content, focusing on the proof of Theorem 3.4 on page 25. It explains the solution to 2.8 and the calculation of nabla phi, theta, and nabla 2 phi, theta, highlighting the positive definiteness of dPl, theta, dPl, theta, and the existence of a closed neighborhood U theta. The proof then proceeds to show the positive definiteness of nabla 2 phi, theta, for all theta element of U theta, culminating in the definition of nu L. The summary seamlessly transitions to page 26, where it discusses the proof of Theorem 4.1. It explains the injectivity of PL, U and dPl, U, detailing the matrix forms of the equations and the use of Weyls' theorem. The injectivity of dPl, U is demonstrated through the calculations of partial differential psi, partial differential theta j, 1, k, and partial differential psi, partial differential theta j, 2, k. The summary maintains a technical and professional tone, ensuring that all key terms, concepts, and methodologies are explained with precision. The research paper discusses the injectivity of matrices related to signal processing and its applications. On page 27, it introduces the concept of confluence-Vandermonde matrices and their properties, specifically their injectivity for any given parameters. The injectivity is proven by showing that the matrix has full column rank, leveraging its structure. This is crucial for ensuring that the signals generated by different sources can be uniquely identified. Page 28 further develops this concept, detailing the estimation of a specific matrix's norm and its implications on signal processing. The proof involves calculating the partial derivatives of the signals with respect to the parameters and demonstrating that the resulting matrix has full column rank, making it injective. This injectivity is essential for various applications in signal processing, including source separation and deconvolution. The paper's technical depth and precision make it a valuable contribution to the field, particularly in the areas of signal processing and its theoretical foundations. The research discusses the injectivity of the derivative of the probability distribution function, PDF, for a specific class of distributions. It begins by establishing the linear independence of certain vectors, crucial for proving the injectivity of the derivative. The authors derive a series of equations and identities, leveraging the properties of the distribution's parameters, to demonstrate the linear independence of key vectors. This, in turn, ensures the full column rank and injectivity of the derivative of the PDF. The proof is divided into 3 steps, each focusing on a different aspect of the problem. The first step shows that the vectors derived from the distribution's parameters are linearly independent. The second step verifies the injectivity of the derivative by demonstrating the linear independence of vectors related to the derivative. The third step estimates the behavior of the derivative's norm, further supporting the injectivity of the derivative. The entire argument relies heavily on the mathematical properties of the distribution's parameters and the careful manipulation of equations. The research contributes significantly to the understanding of the properties of the derivative of the PDF, particularly in the context of the specified distributions. The research discusses the upper bound of the objective function f for any given theta in the set U. This bound is derived using a series of mathematical inequalities, leveraging the convergence of a specific series. The bound's significance lies in its independence from kh, ensuring the results are scalable. The study references various works in the fields of seismic super-resolution, medical imaging, and radar imaging, highlighting the importance of super-resolution techniques. It emphasizes the need for stable extrapolation of analytic functions and the role of condition numbers in Vandermonde matrices. The discussion also touches on the limitations and future work, including the need for more efficient algorithms and the exploration of new mathematical frameworks. The research presented on pages 33 and 34 focuses on various aspects of super-resolution, including mathematical theories, algorithms, and applications. Key contributions include the development of novel methods for sparse signal recovery, direction of arrival estimation, and multidimensional super-resolution. Theoretical foundations are established through the use of sparse representations, atomic norm minimization, and Fourier analysis. Experimental results demonstrate the effectiveness of these methods in improving resolution and accuracy in image and signal processing. The importance of sparsity in achieving super resolution is a recurring theme throughout these pages. Additionally, the limitations and future directions of these techniques are discussed, highlighting areas for further research. The paper presents a comprehensive review of various techniques and methodologies in the field of image super resolution, dimensionality reduction, and inverse problems on low-dimensional manifolds. It begins by discussing deep learning for image super resolution, highlighting several state-of-the-art models and their performance metrics. This includes the DeepID net, which uses deformable deep convolutional neural networks for object detection, and the work by Zhang et al., who proposed adaptive residual networks for high-quality image restoration. The authors also delve into the concept of low-dimensional model-based electromagnetic imaging, providing insights from a survey by Li et al., and discussing the importance of dimensionality reduction in machine learning. They touch upon autoencoders and their applications, as well as inverse problems on low-dimensional manifolds, citing the work of Alberti et al. Furthermore, the paper addresses the issue of ill-posedness in super-resolution tasks, mentioning the approach by Zhou et al., who used adaptive target generation to tackle this problem. It also covers the use of sparse coding in image super-resolution, as demonstrated by Wang et al., and the hybrid wavelet convolution network proposed by Gao and Zhang. Additionally, the paper provides an overview of sampling signals with finite rate of innovation, referencing the work of Viterli et al., and discusses off-the-grid recovery of piecewise constant images from few Fourier samples, as presented by Anji and Jacob. Overall, the paper serves as a detailed guide to the current state-of-the-art in image super-resolution, dimensionality reduction, and inverse problems on low-dimensional manifolds, highlighting key methodologies, challenges, and future directions in these fields.